Welcome to Elementary Real Analysis. Today we are going to explore a fascinating concept called the integral test. If you have ever wondered how we can determine whether an infinite list of numbers adds up to a finite total, you are in the right place. We will build a bridge between the discrete world of series and the continuous world of calculus. Let us start with a simple analogy. Imagine you're building a staircase out of wooden blocks, where each step gets slightly smaller than the last. You want to know if building this infinite staircase requires a finite or infinite amount of wood. Adding up millions of discrete blocks is incredibly tedious. But what if we lay a smooth wooden ramp right over the top of the steps? Calculating the area under a smooth ramp is easy using basic integration. The integral test tells us that if the smooth ramp has a finite area, the jagged staircase underneath it must also have a finite area. Now that we understand the intuition, let us look at the mathematical requirements. To use this test, we must find a continuous curve that perfectly matches our sequence terms at every whole number. But we cannot just use any function. It must meet three strict conditions for all values greater than or equal to 1. First, it must be continuous, meaning no breaks or holes. Second, it must be positive, staying above the horizontal axis. And third, it must be decreasing, meaning it always goes downhill. Only when all three conditions are met can we safely apply the integral test. This brings us to the formal statement of the integral test. If our three conditions are met, the infinite series and the improper integral share the exact same fate. This means they either both converge to a finite value or they both diverge to infinity. The symbol a sub n represents the discrete steps of our series, while f of x represents the smooth, continuous ramp. If the area under the curve blows up to infinity, the sum of the series does too. If the area is finite, the sum is finite. This formula perfectly bridges the two concepts. Before we move on to the proof, let us see this with a concrete example. We want to determine if the famous harmonic series converges or diverges. The terms get smaller, but do they get smaller fast enough? We define our related continuous function as 1 over x. We check our rules. It is continuous, positive, and decreasing because as the denominator grows, the overall fraction shrinks. Since all three rules are perfectly met, we set up our improper integral from 1 to infinity to find the area. Continuing with our calculation, we must remember that in calculus, we cannot directly plug the concept of infinity into an equation as if it were a normal number. So we replace the infinite upper bound with a temporary variable t and take the mathematical limit as t approaches infinity. Next, we find the antiderivative of 1 over x, which from basic calculus is the natural logarithm of x. We then apply the fundamental theorem of calculus, substituting our upper bound t and lower bound 1 and carefully subtracting the two evaluations. Now we evaluate the final limit to finish the problem. We know from basic algebra that the natural logarithm of 1 is exactly 0, which simplifies our expression. As t increases without bound, the natural logarithm of t also grows infinitely large, even if it does so at a very slow pace. Because the integral evaluates to infinity, the area under our curve is infinite. Therefore, by the integral test, the harmonic series also diverges. The sum of its terms will eventually exceed any finite number you can possibly imagine. Let us look at a second example to see what happens when a series converges. We want to test the sum of 1 over n squared. Our related function is 1 over x squared, which again perfectly meets our three conditions of being continuous, positive, and decreasing. To make integration easier, we rewrite the fraction using a negative exponent, making it x to the power of negative 2. Just like before, we replace the infinite limit with a formal limit as t approaches infinity. We now use the standard power rule for integration. We add exactly 1 to the current exponent, turning -2 into -1, and then divide by this new exponent. This gives us our raw antiderivative. We rewrite this back into a standard fraction format, which gives us -1 over x. Plugging in our upper bound t and lower bound 1, we carefully subtract the evaluations. Notice the double negative on the second term, which will turn into a positive addition. We are ready to evaluate the final limit for this second example. As the denominator t grows toward infinity, the fraction 1 over t shrinks down to exactly 0. This leaves us with just the number 1 from the second part of the expression. Because the integral evaluates to a finite number, the total area under the curve is finite. By the integral test, the discrete series must also converge to a finite number. We have successfully used continuous calculus to solve a challenging discrete problem. Now that we have used this formula, let us understand where it comes from, by proving why this magical connection works. We can prove it by comparing the area of rectangular blocks to the area under the smooth curve. First, we draw rectangles where the width of each rectangle is exactly 1 and the height is the sequence term a sub n, starting from x equals 1. The curve passes through the top left corner of each rectangle. Because the function is strictly decreasing, the rectangles stick out slightly above the curve, meaning their total area overestimates the true area under the continuous curve. Next, we look at a second way to draw the rectangles to create a different comparison. We shift them slightly to the right so they sit entirely underneath the curve. In this new setup, the curve passes through the top right corner of every single rectangle instead of the left. Because the function is always decreasing, the rectangles are now completely trapped under the smooth ramp. This means their total area strictly underestimates the true area under the curve. The continuous integral now acts as a solid ceiling for this discrete sum, giving us the second half of our proof. We can now combine our overestimate and our underestimate into one powerful mathematical statement. This combined inequality is the absolute heart of the mathematical proof for the integral test. It shows that the continuous integral is perfectly sandwiched between two slightly different versions of the discrete series sum. The smooth curve acts as both a solid floor for the overestimating rectangles and a rigid ceiling for the underestimating rectangles. By locking the integral between these two bounds, we force the series to behave in the exact same way. Let us visualize the sandwiching effect to make it perfectly clear. Here we can clearly see the sandwiching effect we just proved mathematically. The blue decreasing curve represents our continuous function. The red rectangles stick out above the curve, representing our overestimate, while the green rectangles are trapped underneath, representing our underestimate. Because the area of the curve is locked between these two discrete sums, the series and the integral are forced to share the same convergence behavior. If the curve's area is finite, the green rectangles cannot grow to infinity. Returning to our combined inequality, the final conclusion of our proof becomes obvious. If the integral grows to infinity as the upper bound n gets larger, the series on the left side of the inequality must also be pushed up to infinity. Conversely, if the integral evaluates to a finite number, the series on the left is trapped below a finite ceiling. Because our series only adds positive numbers, being trapped below a ceiling guarantees that it must converge to a finite value. It cannot oscillate or grow forever. This completes our proof, showing exactly why they share the same fate. Let us summarize what we have learned today. The integral test is a powerful bridge connecting the discrete world of infinite series to the continuous world of integrals. By checking if the area under a matching smooth curve is finite or infinite, we instantly know the behavior of the jagged series. Always remember the 3 golden rules. The function must be continuous, positive, and decreasing. This tool is foundational for engineers and physicists modeling complex systems. You now have a deep understanding of how and why the integral test works.